Okay, so yesterday we were talking about uniform circular motion, okay, and we got to the thing about David and Goliath, okay, and how the sling is, a good weapon because it can allow us to use the properties of circular motion to accelerate an object faster than we could just throw it with our arm. Okay, when something moves around and around in a circle, okay, there's a force that is required to keep it there. Okay, that produces an acceleration, which means I can wind something up and make it go quite a bit faster than I could probably move my arm as a whole, okay, to throw it. So, okay, the sling takes advantage of that, takes advantage of the mechanical advantage of a centripetal acceleration, okay, and thus a centripetal force. All right. So here's what we need to look at today. Okay. First thing we need to look at, what things affect the centripetal acceleration of an object. Well, we looked at this formula right at the end of the day. Centripetal acceleration is v squared divided by r. R being the radius of the circle. Okay? So in this situation on the board, okay, this car is coming into a corner whose radius is 320 meters at 28 meters per second. The other car is coming in at 28 meters per second to a corner 3 times wider. Okay? Which one of those cars is most likely to succeed in cornering?
The second one.
Why?
Because the radius of the curve is much larger than the other one.
Right. The radius is bigger on the second one, and radius is on the bottom of the formula. If I'm dividing by a larger number, that's going to make the centripetal acceleration smaller. And that means that the centripetal force will also be smaller, and it's that force, in this case friction, that you're relying on to keep you in the corner. Okay? Now, if I was to alter the speed of those two cars, okay, so let's say they're both on the 960 meter corner. Okay, but one of them takes it at 28 and the other one takes it at 56. Okay, what are the chances of the faster car succeeding in negotiating that corner? Very low, because it's not just faster, it's exponentially greater. Okay, if I double the speed, because speed is squared in that formula, I will need 4 times as much centripetal acceleration, provided by 4 times as much centripetal force. Okay? I am not going to bank on friction being able to do that. Okay? It is highly unlikely that that would be a successful thing for me to do. Okay? Because speed is on the top, and if I make it bigger, AC gets bigger, but it gets bigger exponentially because it is squared. Right? Everybody okay with that idea? So this is something we have to consider when we are taking corners under slippery conditions. Okay? Any increase in speed is going to require an exponentially greater cornering force to be present. Okay? That situation can be exacerbated by possibly having ground that's not even. Okay? Give you an example. Coming out of my neighborhood, okay, when I turn out of my cul-de-sac, okay, this corner that I have to take turning right is actually banked so that this side is lower than this side. It's like the worst possible situation for cornering. Okay? As I go around that corner, not only does my inertia want me to go straight, but there's an F parallel that's also going that way. Okay? So every time I go around that corner, if it's even the slightest bit icy, my back wheel's cut loose and off I go, back end swings right out. Okay? Simply because that's the worst possible situation. Okay? If it was flat, it'd be better. Okay? It'd be a little bit better because I wouldn't have that F parallel trying to take me out of the corner as well. Okay? I just have to rely on friction. Making sense? Okay? Would it be better if the corner was banked this way? Absolutely. Okay? Then I would push into the corner, and what would the corner do? Push back. Now it would push perpendicular to the corner, but a horizontal component of that points back towards the center of the circle. That's why we bank curves. Okay? That's why exit ramps always are banked like this. Okay? They provide a normal force, which means you don't even have to rely on friction. If you go around those corners at the recommended speed, they could be covered in frictionless ice and you'd still get around the corner. If you went slower than that, you'd be in trouble. Where would you go? into the corner. Yeah, we'll talk about that in a little bit when we talk about bent curves. Okay, so this is the situation we're dealing with here. So we will allow Canada's worst driver to educate us a little bit. Anybody ever watch this show?
Yeah.
I like fell down the rabbit hole during COVID and I watched a whole bunch of them. And at first it was funny, and then it kind of became sad. Because there were like two types of people. The ignorant jerks that no matter what you taught them were not going to change their behavior. They were frustrating. And then you got a little bit of joy when they would fail. Okay? And then there was like the people that just weren't very bright. Those were the sad ones. Because they really wanted to learn, but they just weren't very bright. And that was sad. Because some of them really needed to learn and they couldn't. And they tried hard, but that was, as a teacher especially, it was just sad and I had to stop. So, the icy corner.
And the curves.
Okay, so, guys, so here's what we need to get from this, okay? Speed has that exponential effect on your ability to corner, okay? Radius has an inverse effect, so as the corner gets wider, you're able to negotiate it. When we watched him go around the icy corner successfully, he did both of those things. He went 50. He got off the brake. He took the corner wider, didn't steer as much as everybody else. Okay, that increased the radius, decreased the speed. All of those things make it possible to successfully navigate the corner. Okay, making sense? All right, so that's what we kind of need to get out of that. Okay, yes, we know that that as we increase the speed, those things are going to increase as well. All right, so we're going to move on here now to centripetal force. Okay, so we're going to talk about now the force that causes that centripetal acceleration. Okay, lots of forces can act as centripetal forces. Okay, in the case of our ghetto physics roll of tape on the string, what's providing the centripetal force? When I whirl this thing around, what's keeping it in the circle? Okay, what am I holding?
String.
The string. The string is what's keeping that in the circle, because I'm not holding the tape, I'm holding the string. Okay, there's tension in the string, tension is a force, and in this case, that force is always pulling towards the middle of the circle, and thus this thing accelerates towards the center and moves in a circle. Okay, what else can act as a centripetal force?
Gravity.
Gravity. That's why the moon orbits the Earth. Okay, the moon is always accelerating towards the Earth because of Earth's gravity. That's why it moves in a circle. Okay, same with the Earth. The Earth is always accelerating towards the sun. Okay, but it moves in a circle. What else? What were we just looking at? What force is supposed to provide the centripetal friction? Okay, friction is a very common centripetal force. Normal force can be a centripetal force. We were talking about the banked corners. Okay, normal force. Anything that can point towards the center, push, pull, doesn't matter, okay, is going to act as a centripetal force. All right, so we're going to look at a couple of examples of that, okay, here today.
Would air resistance act as a centripetal?
Yeah, air resistance could.
Like if you're using air brakes on a plane.
Yes, but you typically bank the wings, which is what we're going to talk about. Yeah. Okay, so here's the thing we need to realize. Centripetal acceleration is v squared over r. Okay, and according to Newton's second law, net force is mass times acceleration. For something to move in a circle, it has to accelerate towards the center, which means the net force acting on that object has also got to be directed towards the center. So, centripetal force in this unit is our net force. That means it is the vector sum of all the forces acting on the object, and that vector sum has to be towards the middle, but it also means it is mass times centripetal acceleration. Okay, which is going to change our formula a little bit. Centripetal acceleration is v squared over r. So mass times centripetal acceleration is mv squared over r. That is going to be your m times a for this unit. As much as you used m times a in unit 2, you will use mv squared over r here. Okay? Newton's second law still applies. for objects moving in a circle. That doesn't change. Okay? All that changes is now they're moving in a circle. So that net force is always pointed in towards the center. Okay? And it can be the vector sum of all of the forces. So if I've got something moving in a vertical circle like this, okay, is its speed constant?
No.
No. Where is it moving the slowest?
At the top.
Okay, so where does it require the least amount of centripetal force? At the top. Where does it require the most? Why?
Because it's contracting with gravity.
Right, it's counteracting gravity. At the top of the circle, I don't even need any tension in the rope. Because what will act as a centripetal force at the top? Gravity. But at the bottom, gravity doesn't point into the circle, it points out, directly out. So I've got to pull the hardest at the bottom, not only because the thing's moving the fastest, but because gravity is no longer acting in, it's acting out. So I have to pull that much harder to keep this thing moving in a circle at the bottom of the circle. Okay? So it's still vector sum of all forces. Just now it's forces in minus forces out. Okay? When you're dealing with uniform circular motion, so the horizontal stuff, there's only ever one force. There's no force acting out on this thing. There's just inertia. Okay? But okay, in other situations, I might have to look at what other forces would be present, okay, and still do the in minus out. Okay? Everybody all right with that idea? Okay, so that formula is on your formula sheet. We're going to use it all the time, okay, because it's going to be our m times a, and it's still going to equal the sum of all forces. The good news is the sum of all forces in this unit is always easier than it was in the last unit. There's never going to be any like vectors other than in and out. All right, so that makes it a lot easier, right? Because we only have to worry about, is that force acting into the circle or is that force acting out of the circle? Most of the time, there's only one force acting as a centripetal force. So we just say mv squared equals this force. And then we go from there. Okay? All right, so sometimes it's easy to identify the force because you can see it. Okay? You can see it when I was whirling that thing around, it was the string that was holding it. Right? When a car goes around a corner, sometimes that force is less obvious. We don't really see friction. If they're going too fast, we can hear it because the tires will squeal, okay, or something like that. But most of the time, we don't see that force. And of course, we don't see gravity either, right? But it acts as a centripetal force. Now, if gravity is holding the moon in orbit around the Earth, why does the moon orbit the Earth and not the sun? The sun is way bigger.
Because the Earth is closer.
Yeah. Remember, part of this formula is radius. Okay? The moon is beyond exponentially closer to the Earth than it is to the sun. Okay? So it's way more attracted to the Earth because R is much smaller for it and the Earth than it and the sun. Okay? Now, the Earth is also attracted to the moon. So when the Earth goes around the sun, like if this is the sun, we have this vision that the Earth goes around in this nice circle. Right? But it's actually like wobbling around, okay? And that's just when you take the moon into account. You start taking other planets into account, the Earth goes all over the place in its orbit, okay? Because it's constantly being pulled in different directions. It's not the perfect circle we envision. And it's not a circle, it's an ellipse. So there's times of the year where we're closer to the sun than others. What season? Actually, it's winter. Yeah, that's a trick question. I mean, everyone says, I mean, because that's your natural record. Well, closer to the sun because it's hotter. But seasons are caused by the tilt of the Earth, not actually where the Earth is in its orbit. I set you up. I'm sorry, Ben. That was a setup. Okay, so problem with this diagram. It has that on it. There's no such thing as that. Okay? There's no center fleeing force when I'm whirling this thing around and around in a circle. There's nothing trying to pull it out of the circle. Okay? There's inertia that wants to go that way, okay? But that's not a force. That's just the tendency of the object to do that. I'm overcoming that and making it go in a circle. Okay? Unless there was something like actually physically pulling on the tape out of the circle, exactly opposite to me at all times, there would be no centrifugal force. Now, when I was whirling it in a vertical circle, gravity at the bottom of the circle can act as a centrifugal force, a center fleeing force in that case. Okay? All right, so we just want to demonstrate here the effect of different speeds on how much force would be required to keep something in a circle. Okay, so we know my formula is mv squared over r. Okay, I have a 0.9 kilogram mass. It's going 19 meters per second on a 17 meter long line. All right, so if I take those things, so I go 0.9 times, let's clear it all here, 0.9 times 19 squared divided by 17, okay, I get 19.1 newtons. All right, so to keep that thing going in a circle would require 19.1 newtons worth of tension in that string, in that line. Okay, if I swing it twice as fast, okay, so now it's 0.9 kilograms times 38 squared over 17. How many times more force am I going to need? 4. What's your question?
No.
Oh, I put times in there. That's a terrible demo. That backfired. Times 38 squared divided by 17. Okay, 76.44. I'm pretty sure that's 4 times greater than 19.1, but we can double check. Yep, looks good. Okay, everybody all right with that? So speed has that exponential relationship. Okay, then radius, okay, obviously has an inverse relationship, but it's inversely linear. So if I double the radius, I will decrease the necessary centripetal force by 1/2. Okay, so it's a linear relationship there. Okay, and we can see that here, okay, where they do the calculations for the same thing, that 0.9 kilogram mass, moving at 28 meters per second on an 11 meter line, gives us 64 newtons worth of force. That's the short line. Okay, if I increase that radius to 22, the force is cut in half. Okay, so it looks kind of like this. If I've got this tape in a short circle and whirling it at a constant speed, okay, you can see that, you know, there's a fair amount of tension in the line. I'm holding the string pretty tightly. If I double the length, the radius of that circle and make it move at the same speed, I don't have to hold on to that thing nearly as much. Okay, it's going, it looks like it's going slower, but it's actually at the same speed, and I don't have to hold on to this thing because it's a bigger circle. Okay, I don't have to grip it nearly as tightly. Everyone all right with that idea? Okay. So, going around an unbanked corner, so a corner that is level, like most of the corners in town. Okay, what am I relying on to keep me in the circle? Friction. Okay, so if friction is what's pushing me back towards the center of the circle, is it providing a centripetal force? It is. This is the vector sum of all forces part of circular motion, deciding what force or forces are acting as centripetal forces. Most of the time it's just going to be 1. Okay? When we get to vertical circular motion, it'll be 2. We'll never have more than that. Okay? So, in this case, centripetal force is being provided by the force of friction. So can I write this and have it be true? Okay? I mean, we would have done stuff like that in the last unit, right? That's vector sum of all forces stuff. Okay? Now, if the road is not banked, so it's nice and level, what force is normal force equal to? No, it's not equal to 0. The net force would be 0. What force is equal to it? Gravity. Right? Gravity is pulling down. Normal force acting up. Okay? So, I could replace Fn with mg. Okay, I'm going around this corner. I've got an m on both sides, and it's the same m. What happens to it? Does that seem odd? Can a heavier object take a corner at the same speed as a lighter object? Yes. But in the real world, we don't see that because this assumes that the center of both of those objects' masses is in the same place. Heavier objects tend to be taller. Okay? Things that are taller tend to tip more easily because they have more mass or more inertia higher up, okay, which causes a rotational effect that causes tall vehicles to tip more easily than low, smaller vehicles. Everyone kind of follow me there? Okay, so if I had blocks and they were just going around like an air table, okay, and they always had their center of mass in the same spot, a heavy block and a light block would go around in the same way. Okay? In the real world, we don't see that because of the rotational effect of the higher center of mass. Okay? So if you're driving, let's say, like a big moving van or a big cargo truck, okay, you go around a corner, you are not taking that corner at a high rate of speed like a small car because you'll tip. Okay? So tip for not tipping. If you ever have to move and pack a truck full of stuff, where should you put all the heavy stuff? Bottom. Put it in first. There's two reasons for that. Margo, pay attention. Okay? There's two reasons for that. You don't want to lift heavy stuff. Don't put it up high, it'll hurt. Okay? It'll crush things underneath. And secondly, it's way safer to corner if all the mass is at the bottom. Okay? Everyone okay with that idea? All right. So, mass is going to cancel in this situation. Would I be able to calculate how fast I could take a corner if I knew the radius and the coefficient of friction? I could. All right. So this is how they test the cornering ability of cars. Okay? Car manufacturers have an area in their lots that is called the skid pad. It has a circle with a radius of 50 meters painted on it. And they drive the car around that circle at ever increasing speed until it skids out. Okay? And based on that speed, they can rate the cornering ability of the car in G's. Okay? So like G-force. Most passenger vehicles are capable of cornering at somewhere between 0.75 and 0.85 G. Okay? So that means if you were the passenger, okay, and you had your face plastered up against the window because of the driver cornering very quickly, you would feel a force equal to 0.85 or 85% of your mass or your weight pushing on you. Okay? So cars can corner pretty well, provided they're designed with a low center of mass and all of that stuff. Okay? A larger vehicle, like a taller vehicle, like a truck, this number would probably be lower, probably 0.6 something. Okay? A very high-end sports car, that number might be closer to 1 G or even more. Okay? So in a car like that, when you take a corner, you're holding onto the wheel for dear life. Okay? Your passengers are grabbing onto the holy crap bar, okay, on the C-pillar there, okay, and trying not to fly out. All right? So if we want to calculate the effect of traction on speed, we can do that. Okay? We're going to look at a dry, perfect driving condition of where the coefficient of friction is 0.9, and icy conditions where we have 1/9 the friction. Okay, so if we're thinking through this, I have 1/9 as much friction in an icy condition. How much slower do I have to go?
10% slower.
But that's good because you're thinking of the exponential relationship, 81 times slower. But it's actually because it's going the other way. What's the square root of 1/9? 1/3. The square root of 1/9 is 1/3. It's an exponential relationship, but we're going the other way. We're changing the thing that speed depends on, not changing the speed. Okay, if I change the speed, then yeah, if I increase the speed by 9 times, I'd need 81 times more friction. But I'm changing the friction, I'm going to need 1/3 the speed. Okay? So let's just do the calculation. So FC is being provided by FF. That means mv squared over r equals mu times m times g. I'm solving for v. So I'm going to multiply both sides by r, and then m is going to cancel, and then I'm going to square root. So I'm going to be left with this. V is the square root of mu-gr. Mu-gr. Mu-g-r. Okay? So, for the ideal conditions, that's going to look like this. The square root of 0.9 times 9.81 times 50 meters. going to be 21 meters per second, which is pretty quick to go around a 50-meter wide circle. Okay? If I do the icy conditions, now it's 0.1 times 9.81 times 50. Okay? If I do that, it's going to be 7.0. Now, just so you don't think I'm full of crap. Okay, I'll punch it all in here. But so 0.9 times 9.81 times 50. Okay, 21. And 0.1 times 9.81 times 50. 7. Okay, so if I have 1/9 the friction, I must decrease my speed by 3 times. Okay. Is that something we have to remember?
Yeah.
Yes, go slower when it's slippery. That is something you have to remember, okay? It's simple, but we forget it, right? We get in that summer driving mode. The first day it gets icy is a disaster, okay? Because nobody has switched over to winter driving mode yet, okay? And then you see, like, you know, what was it, 2 years ago where the guy missed the corner out here and ended up in the swamp? Okay? Like, dude, what, like, Mr. Dickey and I are like the first 2 people out there, the physics guys, of course, and like, dude, friction, cornering, centripetal force, you fail. Okay, yeah. It's an epic fail. Truck in the swamp.
Weren't there like 2 crashes yesterday?
Yesterday? I don't know. Were there?
Apparently there's one down here and there's one at the 4-way.
Slow down.
And if you go to the HTA as well, they're like go too fast. You just go right through over the road into the ditch.
Oh, out here. Yeah.
Yeah. Same with like little bubbles. So
Yeah. Getting out of the parking lot. Yeah.
Mine's four-wheel drive.
Okay, so this is what we just did here. That's the reasoning. Now, not all curves are flat like that. Okay? Sometimes we bank them. Okay? Anyone ever been on a plane before? Okay? If a plane wants to turn, like make a big turn, what does it do?
Angles.
It angles itself. It banks its wings. Okay? I mean, it's got a rudder on the tail. It can make small turns with the rudder. Okay? But if it wants to make big turns, it dips its wings. How does that help it turn?
A force underneath the wings is pushing it, so it's like pushing it towards the other way.
Exactly. Yeah, wings are designed to create lift. So if the plane is flying level, the force the wings exert is straight up against gravity and the plane can stay aloft. Okay? But as soon as the plane banks, that lift is still there, but now it's angled perpendicular to the wings, which means it has a component that's horizontal now. And that points back towards the center of the circle. As soon as the plane dips its wings, it's going to turn. It doesn't even have to turn the rudder. Banking the wings will cause it to turn because it's changing the direction the force of the wings is exerting.
Isn't that the same with a bike?
Yes. With a bike, when you lean, you're creating more of a force that's angled towards the center. If you ever watch that cycling, the Olympic cycling indoor stuff on those tracks, they can be almost horizontal. Okay? And in fact, the Gravitron, has anyone ridden the Gravitron, that ride? You spin it around and around, you can actually, I don't want to do that. You stand on the wall, imagine I'm standing with my feet up. Okay? Stand on the wall like this, you won't fall because there's so much centripetal force pushing you towards the center that you can defy gravity essentially. I'll show you a video on that on Monday. But when you bank your wings as a plane, what you're doing is using some of that lift as a turning force. But remember, you're using some of that lift as a turning force. What is the plane doing when it turns besides turn? Well, if its wings aren't flat, now its lift is angled. Does it have enough lift to stay in the air? No, it's going to start to drop. Okay? If you see it like in Top Gun when they would put the plane on its side and turn, they're not just turning. In that situation, they're also falling. It's a great way to evade an attacker. It's why every time there's an attack, the guy in the back yells, bank this way or bank that way. Because as soon as they bank, not only do they turn away from the attacker, but they also vertically change their position. Okay? It makes them very difficult to hit. Okay? Because they're changing 2 things about their flight path. Okay? Or you pull the Maverick, right? Which is, yeah, you put the speed brakes on and stop in midair. Okay? That maneuver, if done improperly, is a suicide maneuver. Okay? Because you will create a stall. In order for a plane's wings to make lift It has to be moving forwards. The air has to be going over the wings. If you slow down, you will stall. That means the wings don't create lift, and you just fall out of the sky like a rock. Okay? It's very dangerous. It actually is what happens with the Tomcat. It can get into the death spin, they call it. Okay? If one of its engines goes out, there's enough space between those engines that it creates a turning force, so they can throttle back one engine to help them turn, but if one goes out, it can put them into that spiral where now they're spinning like this and the wings don't create lift and they fall out of the sky as well. It can be a kind of a big problem. And of course the infamous cockpit problem, right? The killed goose. Yeah. Okay. Yeah. There was a really bad design for that, and the cockpit pyrotechnics would not get the cockpit out of the way, and the co-pilot or the weapons officer would hit the cockpit and break their neck when they ejected from the plane. So yeah, dangerous stuff. All right, so is that making some sense? This whole banking thing, okay? And it's also why NASCAR corners are banked the way they are. Okay? Those NASCAR guys can go around those corners a lot faster because the corners are banked. Unless you're really smart, like the guy I'm about to show you. Has anyone seen this clip where the guy, well, they call it now after he did it cheating, but I call it using physics and winning. Okay? The guy that uses the wall. Yeah. So he said, the corner doesn't provide enough normal force with its bank, so I'm just going to slam my car into the wall and go as fast as I can, floor it with my car against the wall, because the wall will push me towards the center. And he passed like 5 cars on the left. His car was destroyed. Okay? You can only do it on the last corner because your car won't last. Okay? But it was a genius play.